I welcome you to today's introductory colloquium on the science topics of one of the planned ECD STAR workshops for 2020 that has been deferred to 2021 because of the COVID-19 pandemic. The aim of this colloquium series is to introduce and publicize the science case of the workshop to a wider audience. Today's presentation, given by Ralf Rapp from Texas A&M, is on the workshop Heavy-Flavor Transport in QCD Matter, originally planned for the week starting from February 14th, 2020. The talk focuses on heavy hadrons, including charm and beauty quarks, as probes of strongly coupled strong interaction matter, and these particles are produced in ultra-relativistic heavy-ion collisions. The goal of the workshop is to arrive at a quantitative extractions of pertinent transport properties. For this, various components of the theoretical description have to be brought under control. The workshop will bring together leading theorists and experimentalists working in the field of heavy ion physics and merge and continue larger scale efforts at this goal of providing a comprehensive description of these reactions. Let me briefly introduce the speaker to you. Ralf Rapp received his PhD from the University of Bonn, and after several postdoctoral and research assistant professorships in Jülich, Stony Brook, and Nordita, he moved to Texas A&M in 2003, where he's a full professor of theoretical physics since 2010. His research interests are in the theoretical description of QCD matter under extreme conditions and resulting experimental signals in heavy ion collisions. He is most well known for his work on electromagnetic probes such as dileptons, where he has made groundbreaking predictions that turned out to agree quantitatively with measurements. He's one of the international leaders in the field and a well thought after speaker at international conferences, workshops, schools, and so on. And he has also won a variety of prestigious rewards, among them noteworthy the Bessel Award of the Alexander von Humboldt Foundation. So please welcome Ralf Rapp.
Welcome to the ECD STAR colloquium on heavy flavor transport in the Quark Gluon Plasma. This was indeed the topic of a workshop that was scheduled at the ECT for last February and had to be deferred to next year. And we are therefore happy that we can share the ideas and objectives of this research in this colloquium. And in this sense, I'm giving this talk also on behalf of my co-organizers of this workshop. So let's start with some basic properties of the strong interaction as described by quantum chromodynamics, whose Lagrange is written here in terms of the quark and gluon degrees of freedom, as well as their interactions. One of the key features of this interaction is that the coupling constant for scattering processes, has this remarkable feature of increasing with decreasing momentum transfer in the interaction, or in other words, with increasing distance. Indeed, this coupling becomes very large at a scale of about 1 GeV, and this is where we expect a transition to a really strongly coupled system, also sometimes referred to as strong QCD. It is in this region where the very fundamental non-perturbative effects of the strong interaction occur, in particular the confinement of the colored charges into hadrons, as well as the mass generation of the hadronic degrees of freedom in the vacuum. Now we can get more insights into this non-perturbative behavior when we look at the potential between two heavy quarks, two static color charges. And this is plotted here as a function of distance. And we see, indeed, at short distances, we have this characteristic Coulomb behavior, essentially perturbative, relatively small coupling. While at distances roughly larger than a quarter Fermi or so, you see the onset of this linearly rising potential, truly non-perturbative effect. In fact, it is very suggestive for confining force, and in this sense, maybe one of our best theoretical evidences for confinement in nature. Now, by now, this potential is really well established, and the symbols here are lattice QCD computations. And we also, in fact, from 30 years ago, when the Quarkonia, the heavy Quarkonia were discovered, already inferred a phenological form of this potential, which agrees very well with the lattice data that does an excellent job in describing the observed spectroscopy of these heavy Quarkonian bound states. Now, the next step then is to go to QCD Matter, or in other words, the QCD phase diagram, as a function here plotted of temperature and chemical potential. Now, we clearly expect that these non-perturbative features that I just described for the vacuum physics also play a key role in governing the phase structure of QCD Matter. And a priori, this becomes a rather daunting task, as also many body effects like superconducting phases may occur. But here we really get help from experiment, and it's quite fascinating that using heavy ion collisions with varying energy, we can actually cover a good part of the phase diagram through these experiments. And indeed, very remarkable results have emerged, in particular here on the final temperature axis from the high energy colliders, LHC and RHIC, where we found, for example, that the medium, the QCD medium, is a very strongly coupled one with a, for example, shear viscosity that is very close to the expected lower bound given by quantum mechanics. And this is indeed quite different to naive expectations of a non-interacting Quark Gluon Plasma, which may come in at very high temperature. Now, even so, we still do not really understand what are the microscopic interactions that drive these remarkable properties of the Quark Gluon Plasma and how they exactly relate to the transitions of the deconfinement and higher symmetry restoration. So let's have a look what numerical solutions of the QCD partition function can tell us about these matter properties. For zero chemical potential, they can be carried out with high precision. And here are shown two examples of results from these numerical simulations. On the left-hand side, we see the thermodynamic quantities, state variables, pressure, energy density, and entropy density as a function of temperature. And indeed, there seems to be a transition from a system governed by hadronic degrees of freedom to a system that is much closer to the expected Quark and Gluon degrees of freedom. However, notice that we are still far, even at relatively high temperatures, still far from the limit of non-interacting massless quarks and gluons. And this is, of course, suggestive for a large contribution from interactions. Now, lattice QCD can also measure very well the partition function of a heavy quark pair embedded into the medium. And this is shown on this plot. Now, at zero temperature, this free energy actually just becomes the potential that I discussed earlier, shown by the dashed line. But at final temperature, we see that indeed there is sort of an expected screening of this free energy or potential. It's not really a potential, as we'll see later. But even so, in a way, the screening is remarkably weak, if you wish, because even at temperatures that are already well above the transition temperature, say of 160 MeV, the free energy still shows rather prominent non-perturbative effects in terms of this linear part of the potential still being present. Now the question then is, can we somehow use this potential and probe it probe it in the medium? So how can we probe the QCD force in the medium? Well, the first idea would be, of course, to apply to the heavy quark sector. So can we at least then evaluate the consequences of such an in-medium force on the properties of heavy quark transport and the corresponding spectral functions? And if we achieve that, can we then transfer that knowledge on the interactions that we gain from such a program to the properties of the QGP at large, its transport and spectral properties? These are sort of the basic questions that we have in mind when we pursue this kind of research. So let's have a quick look at what the issues are when we look at heavy quark systems in the QGP, starting with the bound set, the QQ-bar bound sets, Quarkonia. This Quarkonia, in fact, had been proposed as a probe of the Quark Gluon Plasma about 30 years ago. And the idea being that the potential is expected to be screened, so this will affect the binding energy, even drive it to zero at some point, and then these Quarkonia dissolve, and there would be a suppression signature in the experiment. However, it turns out that the Quarkonia can also be dissociated while they are still bound, because there's a finite rate for dissociation due to inelastic collisions with the medium. So in the more general context, these quantities are, of course, embedded in the quarkonium spectral functions. And here you see one example of the calculation of these quarkonium spectral functions in the vector channel. The gray bars are the vacuum masses of the J psi and the psi prime. And then you see, as you increase temperature, the psi prime really dissolves, disappears from the spectrum rather quickly, while the J psi, being much stronger bound, may actually survive for quite a while in the Quark Gluon Plasma. Again, this is a highly non-trivial task to do such calculations in a reliable way. And therefore, one might ask whether one can simplify the problem. If you think about it, what you're really trying to understand is how the heavy quarks inside the bound state interact with the plasma. So why not take away one of the heavy quarks and then ask the question, maybe simpler question, what are the properties of a single heavy quark in this medium? And again, what we'll see is that the heavy quark mass being large compared to the typical temperature scales that we're dealing with will lead to a lot of simplifications in the theoretical treatment. And in this way, give us really a rather clean window, maybe the cleanest we have, on understanding, possibly understanding how this force manifests itself in the medium. So let's have a quick look at the problem of drum and bottom quarks in the Quark Gluon Plasma, starting out at low momentum. At low momentum, because the heavy quarks are heavy, there's very little energy transfer into interactions. It's parametrically suppressed compared to the momentum transfer. And therefore, these interactions are manifestly elastic at low momentum. At the same time, the momentum transfer, being of order of the temperature, is much smaller than the heavy quark mass, or typical momenta of the heavy quark. And therefore, we really have a situation which is akin to the Brownian motion problem, where this heavy quark propagates through the medium and receives a lot, possibly a lot, but small kicks from the medium as it goes along. So this is a nice analogy using the heavy quarks, if you wish, as Brownian markers of the Quark Gluon Plasma. Another practical benefit from the heavy quark sector is that the thermalization, because of its heavy mass, is delayed parametrically by a factor of quark mass over temperature, which can be large, 5 for charm, and maybe 15 for bottom quarks. And that then means that the thermalization times become comparable or even larger than the typical lifetime of a heavy-ion collision, where we want to investigate these modifications of the heavy quark spectra. And therefore, the finally observed heavy quark spectra may very well contain a memory on the interaction history, and in this way provide, in fact, a gauge of their interaction strength as they propagate to that fireball that is formed in heavy-ion collisions. If that is so, we really have a rather direct access to a fundamental transport coefficient, namely the heavy quark diffusion coefficient, the spatial diffusion coefficient, which is really just the one that we all know from the Brownian motion problem as a propagation in a diffusion in coordinate space. Once we have this, we can actually try to make connections to the other transport properties of the Quark Gluon plasma, such as the specific shear viscosity or even electromagnetic conductivity. The idea being that the interactions that drive the properties of the heavy quarks should, of course, be very much related to the interactions that are responsible for the transport of energy momentum or charge. Now, the key ingredient in this are the scattering rates of the heavy quark. And in a quantum language, these are nothing but the collisional widths of the particles. The question you can then ask is, if the widths become large, do we still have good quasi-particles in the medium? Now, I'm going to make a little estimate here based on what we'll see later. Let's say that this dimensionless scale heavy quark diffusion coefficient is about 3. And then a little calculation reveals that the collisional width of the heavy quark is actually 1 GeV, about 1 GeV, and that is larger than the typical temperatures we encounter. While it is still smaller, sort of smaller than the charm quark mass, definitely smaller than the bottom quark mass. So we may actually encounter a situation where the heavy quarks are still reasonably good quasi-particles, but the widths are so large that the thermal degrees of freedom in the Quark Gluon plasma, the light partons, may actually may not be good quasi-particles anymore. And if you want to, of course, evaluate that, we need to include the non-perturbative effects. We know the color-Coulomb interaction alone cannot do it. And but as I will argue, there are ways we can do that using these potential interactions that I introduced earlier. Another benefit of the heavy quarks is that they are a very good probe of hadronization. The charm quarks, say, as they diffuse to the Quark Gluon plasma, that is universal. But once they convert into hadrons, then we expect differences in the spectra of the hadrons to emerge. And these differences then are, of course, precisely due to the interactions that happen at the hadronization transition. Now, what happens at higher momenta? Now, at higher momenta, quarks eventually will start to be able to radiate gluons. In other words, inelastic interactions or radiative interactions coming. Still, in these radiated diagrams, the basic building block is that of an elastic interaction, in this case, a half-off-share bond, so that you provide energy for the radiated gluon. The widely discussed transport parameter in the high PT context is that is the so-called jet transport parameter Q hat, which characterizes the transverse momentum broadening as the quark propagates per unit path length of this quark. Now, key features in the heavy quark sector that are different from the light quark sector is that the heavy quark mass actually suppresses the emission of forward gluons, but it also there's also suppression of coherence in that radiation, simply because the heavy quarks get on shell much more quickly, and therefore a coherence of multiple emission is suppressed relative to, say, light partons. And this then raises several questions. Maybe the most obvious one, that where is actually this transition scale in the heavy quark sector from the elastically dominated to the radiatively dominated regime? And in this regime where the radiation starts to become important, one actually expects a mass hierarchy, namely that the energy loss due to radiation for the bottom quarks is smaller than that of the charm quarks, which is smaller than that of the light sector. On the other hand, at some very large PT, where the mass effects should go away, we should expect that there's a degeneracy, again, between those particles in their energy loss characteristics. And indeed, even for the heavy quarks, at some point, the coherence should set in. And typically, that coherence is characterized by this quadratic path length dependence in the energy loss, which can possibly be tested in heavy-ion collisions. Also, in the radiated sector, we need to worry, of course, about the non-perturbative effects, both in the interaction kernel, but maybe also for the emitted gluons. Okay, so that was the sort of general introduction to the problem. The remainder of the talk is organized as follows. I will start out with a discussion of what kind of transport approaches have been used to describe the propagation of heavy quarks in the fireball of a heavy-ion collision. Then I discuss what interactions people have been using to determine or calculate the transport coefficients that are needed in this description. We also have to worry about the hadronization, as I mentioned. Of course, also an opportunity to learn about hadronization. And in the last section, I will then come to the current status of heavy-ion phenomenology, discuss some basic features of the data that we have so far, and what it implies for the transport coefficients. So let's start with the transport approach, or approaches that have been used. So the schematic picture is the following. We start out, so this is a sketch of a time evolution of the fireball and heavy-ion collisions. There's the heavy quark embedded into that. Now, one thing we need is the initial condition for the heavy quark spectra that we can probably get from proton-proton collisions where we don't expect the fireball to form. And then in the very early phases, there are probably some pre-equilibrium fields before the system thermalizes. But this is a relatively short time, as we know from heavy-ion phenomenology, and indeed the medium seems to thermalize pretty quickly. And then indeed the most important component in what modifies the charmed quark or bottom quark spectra in their propagation is their interactions within the Quark Gluon Plasma, until they transit into hadronic degrees of freedom, which even those can rescatter later in the hadronic phase, presumably with some weaker interactions. Now, one point I want to make here is due to the fact that, as I showed on the previous slide, the transition in QCD, at least at zero chemical potential, so on the temperature axis, is a crossover. We should also expect that there's a continuity in the interactions that the charmed quark undergoes. So in other words, the interactions which ultimately hadronize the charmed quark should be gradually building up as it approaches the transition temperature. And as such, it is very suggestive that the confining interaction that color neutralizes the quarks should still play a role, should already play a role before the hadronization occurs into the quark gluon, already in the Quark Gluon Plasma. So there's no continuity, there is no discontinuity in interactions, and hadronization and diffusion, at least at not too high temperatures in the QGP, should be related. Of course, logical or the suggestive candidate for that is the confining interaction that may have remnants in the QGP. All right, so what are the actual transport equations that people use in this field? One is the semi-classical Boltzmann equation for the heavy quark, for the evolution of the heavy quark phase-space distribution. It is based on the collision term here, which explicitly accounts for the scattering of the quarks on the medium constituents, also modeled as quasi-particles. And as I said, this is based on a semi-classical approximation. The other option is the Fokker-Planck equation that has been pursued. And you can derive that from the Boltzmann equation in the limit of a small momentum transfer relative to the momentum of the test particle here, the heavy quark. And that is a good approximation for charm and bottom quarks, as their typical momentum is parametrically larger than the temperature. Now, as it turns out, in a way, the Fokker-Planck equation can also do a little more than the Boltzmann equation, because when you evaluate these transport coefficients A and B here, you can actually formulate them in a way that does not require the medium to be one of quasi-particles. In other words, you can do the full off-shell integrations over the medium constituents in calculating these transport coefficients. And this makes the Fokker-Planck equation actually very well suited for a situation where the scattering rates are large, in fact so large that there may be no more quasi-particles in the medium, while the heavy quarks, of course, are still required to be quasi-particles as you simulate them along these transport equations. All right, so the key ingredient then to the Fokker-Planck equation are its transport coefficients A and B on the previous slide. Let's have a closer look what they correspond to or what they mean. Now, the first one here is in the gamma is the thermalization rate. It's the scattering rate of the heavy quark weighted with the momentum transfer, and that you can then rewrite in terms of the 2-to-2 scattering matrix element as a key ingredient and an angular weight that comes from the momentum transfer. In fact, this thermalization rate is nothing but the inverse thermal realization time that I'll come back to later. The second term involves the momentum diffusion coefficient, and this is really the next higher moment in the momentum transfer, otherwise the same kind of transition rate from with momentum transfer Q. And the beautiful thing here is that these two transport coefficients are actually related to each other. Their ratio is essentially the temperature, and that is indeed a requirement for consistent setup of this equation, so that indeed in the long time limit, the heavy quark will thermalize at the same temperature than the ambient medium. There's also a direct relation to this spatial diffusion coefficient that I mentioned earlier. It is essentially proportional to 1 over the thermalization rate. So if you have a very strong interaction, a large thermalization rate, that diffusion coefficient will be small. In other words, due to the multiple interactions or scatterings, it cannot propagate very far spatially. And then there is, in principle, this idea of relating that heavy quark diffusion coefficient to other transport properties in the medium. Now, the key ingredient in evaluating or calculating these transport coefficients are the heavy-light scattering amplitudes. So let's come to discussing what kind of interactions could drive these could be used for calculating these scattering amplitudes. Now, the first thing you can think of, and that has been done also about 30 years ago, is to use the simple Born diagrams for the scattering of the heavy quark on the medium partons of gluons and quarks. It turns out that this T-channel exchange diagram with the gluons is actually the dominant contribution. In the vacuum, this has an infrared singularity, but in the medium, it is naturally regularized by this screening mass that enters into this propagator and makes this diagram actually well behaved. Still, because the T is in the denominator, this momentum transfer, which is proportional to the scattering angle, and these diagrams, these T-channel exchange diagrams, the dominant ones, are dominated by forward scattering, and they are not very effective in turning around the angles, in other words, in the thermalization, and therefore a straightforward calculation of the associated thermalization time leads to very large thermalization times, even for charm quarks at relatively high temperature and relatively high coupling constant of up to 20 Fermi over C or even more. Now, there's in a way more bad news for the perturbative approach here, in that the calculation of the next leading order to these scattering diagrams or to the transport coefficient really shows a very bad convergence behavior. Here you have a quantity which is essentially that thermalization rate, and you see when you start from the leading order result, which is sort of this dashed line here, and calculate the next leading order correction, even for a coupling constant as low as, let's say, even 0.1, there's a very large correction, let alone if you go to more realistic coupling constants where the correction can be factor 10 or more. So really, even without invoking any non-perturbative effects, the convergence is very bad, and you cannot really get any reliable estimates for what we think are realistic coupling constants. So you have to do better. One way of doing this is to say, okay, I'm not so worried about the microscopics anymore, but I will use these Born diagrams as an effective interaction gauge, and I will introduce a running coupling constant, in fact, in these diagrams here on the vertices. And I will run the coupling constant not to the thermal scale, but to the debye mass, which after all governs, regularizes the soft behavior of this scattering diagram. So in addition, the debye mass may be much smaller than what you think if you do a hard term loop calculation and matching the soft to the hard part. Now, what you get out of such a calculation is that indeed the thermalization time becomes much faster by about a factor of 10 over the baseline perturbative estimate down to 2 to 3. That really puts it now in the realm of the times of a heavy ion collision. But of course, we are not really in the perturbative regime here. So this approach does not really tell us about necessarily what are the relevant interactions. So for that, we have to resort to other methods, and in particular, carry out resumations. You know how to carry out resumations at least in the approximation that leads to this T-matrix equation. And this T-matrix framework, in fact, can be generalized in quantum statistical framework to a rigorous thermodynamic framework or theory. So here is the basic equation for the T-matrix consisting of a potential and the propagators here of the heavy and the light quark in the intermediate state. In the quantum statistical framework, these propagators will re-interact with the medium, so they are characterized by an in-medium self-energy. Now, this in-medium self-energy you have to calculate again from the T-matrix. So you see that you actually facing a self-consistency problem, which, however, can be typically solved by numerical iteration. The other key ingredient is this potential here. Now, the question is, how can we now relate this potential to the information that we possibly have from lattice QCD? And I'll come to that in a moment. First, before going there, let me show you some typical results that you get for the scattering amplitude. If you implement an in-medium potential and carry out the self-consistency procedure, then you find that indeed close to the critical temperature, you have this large, very large scattering amplitude leading to, in fact, the formation of D-meson-like resonances. That should not be surprising because as you go lower and lower temperature, the potential should approach that of the vacuum. And if it's a realistic potential, then it should produce the vacuum D-meson mass. And indeed, this peak here is close to that vacuum D-meson mass. Also in this approach, you get rather small thermalization times down to maybe 3 to 4 Fermi over C. And you also find that this thermalization time does not really decrease with temperature because you're losing interaction strength. These resonances dissolve, and that sort of is compensated by the increase in the density of the medium, so that at the end of the day, the thermalization time is more or less actually constant. Now let me come back to the question of the potential and how it is related to the free energy that I showed on one of my first slides. It turns out the free energy can be calculated from the Quarkonian spectral function sigma here as an integral and log, where that spectral function here is in a sort of a hybrid representation as a function of energy and distance. And it involves as the key ingredients, well, the potential, heavy quark potential, and the single particle self-energies. Now, you can easily convince yourself that if the self-energies are small, or if the imaginary parts in particular are very small, and this becomes a delta function, then actually inserting that delta function, the free energy equals the potential. So in other words, yes, there is a limit where the potential is equal to the free energy. It's a limit of weak interactions. However, if the imaginary parts here are large, then this is no longer the case. And what turns out is that the potential that you find to describe the free energy in the presence of large imaginary parts is actually driven away from the free energy and becomes significantly larger or stronger than one would expect from the free energy. So large imaginary parts actually imply that the potential is larger than the free energy. And that even makes more pronounced these long-range remnants of the confining force. Now, this is a calculation where this is carried out self-consistently. You're describing the free energy. It's a strong interaction. You get out this relatively strong potential. You can further test such calculations by other pieces of lattice information, like these Euclidean correlation functions that you can calculate from the spectral functions that implied in these calculations, and indeed that provides some further rather quantitative constraints on your setup. So there's a way, the bottom line here, there is a way that you can really use lattice data to get a quantitative handle on the potential of the heavy quarks in the medium. All right, now let me make a few comments about how the calculation of the transport coefficient relates to the ambient QGP medium. Now, in principle, what you would like is that the medium, that the properties of the medium that you use to calculate the transport coefficient are consistent with the interactions that you use in the heavy flavor sector. But that is actually not so trivial. So there are various degrees of approximations that have been used. The simplest one is indeed you use massless quarks and gluons for your medium. But from that we already know will overestimate significantly the equation of state. So it will really, at a given temperature, overestimate the effect on the transport coefficients because you have many more degrees of freedom at a given temperature than you should have based on what we know about the lattice QCD equation of state. You can do the next step and include perturbative corrections. And that works surprisingly well. It generates these effective quark and gluon masses, and that works surprisingly well down to relatively low temperatures, maybe 2 TC or so. But it does lead to overestimate still when you're getting closer to TC. So then you say, okay, I take a more effective approach and adjust the quasi-particle masses or the coupling constant so that I match the equation of state. Then you at least have a consistent description of your equation of state and the degrees of freedom you use to calculate the heavy quark transport coefficients. Next step is to actually include widths in this description for the particles in the medium. That has been done in so-called dynamical quasi-particle approaches where the typical widths are moderate, I would say. They're still significantly smaller than the actual masses of the quasi-particle. On the other hand, as I argued in the T-matrix approach, you can actually do calculations where you have very large width and the medium is not that of a quasi-particle anymore. You can calculate the thermodynamic quantities and the transport coefficients using full spectral functions of the medium degrees of freedom. So let me quickly show some results for two of those approaches. One, the quasi-particle model that has been worked out by the Quarkonia group in the Heavy-Quark context. And you see, if you look at how the coupling constant behaves, it is near realistic values of alpha S of 0.3 or 0.4. The temperatures maybe down to 1.5 TC, and then it really has to go up a lot so that you get the decrease here in the equation of state correctly and consistent with lattice data. And as a consequence, then also these quasi-particle masses really become very large as you approach TC. On the right-hand side, you see a result of the T-matrix approach, where you calculate the free energy based on full spectral functions. And you see that indeed at high temperatures, the major contribution is that from the quarks and gluon degrees of freedom. But as you go down toward TC, there is this interaction contribution that becomes, in fact, the dominant piece eventually. So how can we understand it? Well, we can look at the underlying quark spectral functions and the underlying scattering amplitudes, and you see indeed at high temperature you have reasonably well-defined quark quasi-particles, but at low temperatures you really get actually a remarkably large widths here. And in fact, this is not the quasi-particle peak. This is a collective mode that builds up on a very broad quasi-particle peak that actually suppresses the contribution of the quark degrees and gluon degrees of freedom to the partition function, and rather what takes over are these resonance-like states that you dynamically build up and that come in at a typical mass, like say of the meson, say a rho meson. So these calculations really give you a transition in degrees of freedom by melting the quark quasi-particles and building up pre-hadronic bound states, if you wish. Okay, so let's come to the problem of hadronization now as the next step in the evolution of heavy-ion collision. And again, there are two basic approaches here. One is the well-known approach of fragmentation, that if you have a high-energy jump quark, it has enough energy. It has to color neutralize, so it will fragment into several partons and then form a color neutral charmed hadron. And the nice thing about it is that this is in principle supposed to be a universal process and not depending on how you produce that quark, and thus given by a universal fragmentation function from the charm quark into the hadron, depending only on the momentum fraction of the hadron relative to the incoming quark. And it has been indeed applied to both E plus E minus collisions or also to hadronic collisions as long as you go large enough PT, and it should be universal, independent of the surroundings because it's in the vacuum. The other hadronization approach that has become very popular over the last 10-15 years in heavy ion collisions is that of recombination or coalescence of a quark with surrounding quarks that exist in your environment. There are, of course, good reason for that, because in a heavy ion collision, when the system hadronized, there are lots of thermal partons around, and that may, in fact, be a more efficient process to hadronize your quark into a hadron. You can do the two-body pieces that give you meson, or even for three-body to give you charm baryons. Now, clearly, that depends on the environment. It can be different, say, in a heavy ion collision than in a proton-proton collision, where there's much less surrounding phase space. And it typically has been implemented in two variants. One is the instantaneous coalescence based on essentially spatial wave functions of the hadrons, as well as a resonance or recombination approach, which is carried out in momentum space. Let me briefly elaborate on both approaches. The instantaneous coalescence model is really a 3D integral convolution over the quark spectral functions with the Wigner function for the produced hadron, and the Wigner function then involves sort of a size parameter sigma, which is usually associated with the radius of that hadron, and in principle it's of course different for each hadron. One problem with these approaches is, since you're really restricting the calculation into 3 momentum space, energy conservation is actually not satisfied, and that causes challenges for establishing the equilibrium limit for the produced hadron distribution functions, both chemically and thermally. Now, in the resonance recombination model, which has been derived actually from the Boltzmann equation, you formulate the formation of the meson distribution function in terms of a cross-section or scattering amplitude based on the overlap with the underlying quark distributions in the medium. Now, it seems there's also a 3D implementation here, but it's really this cross-section here which has a width that conserves energy in the process. So this cross-section times the relative velocity is actually nothing else but the scattering amplitude squared. Again, due to its finite width, you do conserve energy in the process. What is also nice that this cross-section, or this scattering amplitude that figures here, precisely makes contact to the scattering amplitudes that you use in the diffusion part of the problem. Quite naturally, when resonances occur, these resonances serve as your facilitator of the hadronization process. In this approach, you can show that you can precisely satisfy the equilibrium limits. And therefore, in particular for low PT, it is in principle a more reliable one. Okay, so now let's come in the last 10-15 minutes to some heavy-ion phenomenology in the heavy quark sector. Let's start with the schematic picture that you can have in mind to guide our intuition. So we have these high-energy incoming nuclei, they collide, probably produce rather quickly within a Fermi or so, this blob of Quark Gluon Plasma that then violently expands for about 5 Fermi, transits into hadronic matter, and then that hadronic matter expands for another 5 Fermi until you finally reach a freeze-out where the particles rather abruptly decouple to the final range of the strong interaction. An experiment that seems to be a daunting task, but it's actually a good thing because the more particles you have, the better chance you have for thermalization and making systematic analysis of thermal properties of the system. So what's the role of the heavy quarks? Well, you embed the heavy quarks in this environment. You produce them in the very early phases with a controlled spectrum that you can get from proton-proton collisions, and then you let these quarks propagate, diffuse through the Quark Gluon Plasma, you hadronize them, and then in principle you have to still diffuse those charmed hadrons through the hadronic system. So this is really based on the idea that the heavy quarks with well-defined initial condition can be used as Brownian markers of this fireball evolution, including its hadronization into different hadronic states. Now, key ingredient other than the heavy quark transport that I didn't discuss yet is that you have to have a realistic space-time evolution of the fireball as a whole. This is something that I will not discuss in this talk. I will simply assume that the models that I'll be about to show results of have done their homework, and that is of course indeed true. On this fireball evolution part, hydrodynamic evolution, for example, in most cases. So let me briefly introduce the two main observables, in particular also in the heavy-flavor context, that are used to quantify the properties, the changes in the heavy quark spectrum relative to proton-proton collisions. The first one is really just the ratio of the spectrum of the heavy flavor particles that you observe in an AA collision to that in a PP collision. So directly, modification of the spectra right there. Of course, you produce many more quarks in heavy-ion collision, so you have to account for that by taking out that sort of extra number that goes with the number of primordial nuclear-nuclear collisions. Each of one can, in principle, produce a heavy quark. Now, typically, this what is called nuclear modification factor, RAA, is a very useful quantity at high PT, where energy loss of the quarks would lead to a reduction in this RAA. So that's a famous, if you wish, jet quenching signature at high PT due to the presence of the medium. The more subtle, somewhat more subtle, but no less valuable observable is related to the angular distribution of the particle spectra. So you can expand the particle spectra in terms of harmonics in the azimuthal angle. So let's look at a little cartoon here. Let's say we have this non-central collision. Go back here. You have a non-central collision. You form this elliptic overlap zone, and then if it thermalizes, you will have larger pressure gradients in plane than out of plane, so that at the end of the day, there will be particles will be more pushed in this in-plane configuration, and that will lead to a positive coefficient here. If phi is 0, then it's in plane, or if phi is 180, and also again maximal. So this V2 coefficient as function of PT tells you that there are more particles pushed in this direction than in that direction. And it's of course perfectly suited for heavy quarks also. When you embed them and they get dragged along with the bulk of the medium, then they should also inherit a V2 due to the drag along the medium, and the question and the amount of V2 that the heavy quarks then pick up should in principle be a direct reflection of the interaction strength as they get dragged along with the medium. All right, so let's look at these observables here again. In the upper panel, the RAAs, in the lower panel, the V2s of D mesons in this case that have been observed in left panel for RHIC and right panel for LHC. And there are some basic features that you can glean from the data and that tell you already very interesting information. So first of all, you see, certainly in the calculations, but also in the data, there's this kind of maximum structure, this bump structure in the RAA of heavy quarks. Of course, you have the high energy loss, but you also have this maximum structure. And indeed, this bump, if you wish, at least in the theoretic calculation, is nothing but reflecting, in a way, the thermal velocity, the velocity that the quarks have as they move with the interacting medium. Of course, it will be smeared by thermal motion, but in principle, if there would be a very accurate measurement, you could really extract the velocity with which the quarks move along with the medium. And then, of course, you have this transition to the energy loss regime at high PT. At the same time, the V2 values that you observe for the D mesons are remarkably large. They are actually not very far from what you observe in the bulk medium. That was really a surprise that the charm quarks, being relatively heavy, can pick up such a large V2 from being dragged along with the medium. And indeed, taking together these RAA and V2 observations, we can really infer that there must be a very strong coupling in the medium, in particular close to TC, because the bulk medium takes some time to build up the azimuthal symmetry. And once it builds up, then it is most effective for the heavy quarks to pick it up. So it's really, they need a large interaction strength relatively late in the QGP evolution, where the bulk medium has built up a lot of this V2 already. And a very important facilitator in picking up this collectivity is indeed this recombination with directly the light degrees of freedom that have this azimuthal asymmetry built into them at later stages, say right around hadronization. Another very interesting feature is seems to be indicated already here by LHC data here shown for Alice, but very similar also for CMS data. You have this rise and then the maximum value, and then you have a gradual transition leveling off to a plateau. In fact, the plateau is not a collectivity really, it's rather path length dependence of the heavy quarks. So it's a relatively constant value of 5 to 8% or so. But then as you go down in momentum, you're really starting to pick up the collectivity from the expanding medium, not the path length dependence, but the collectivity. So this you can then identify in a way as a transition region from the elastic to the radiative regime. And you can make similar arguments about the RAA, and it turns out from current data that at about 10 GeV, radiation dominates. You have this relatively flat RAA, it rises a little bit, but also relatively flat V2 here. So these are already quite some interesting information you can extract from the data qualitatively. And then most of the calculations do a pretty good job by now in reproducing these features. Now let's look at another piece of information now, looking at different hadron species, charm hadron species. Possibly revealing us information about hadronization process, as I argued before. And indeed, if you look at the, say, the RAA for the D mesons in green, for the DS in orange, and for the lambda C in black, you do see significant differences in the low PT regime, while again, at the scale of about 10 GeV or so in momentum, they seem to be more or less degenerate, but then you have these onset of different RAAs, and which we believe is indeed due to different, due to hadronization effects. In particular, the enhancement of the DS was actually predicted by model calculations as being due to coalescence with the strange content in the Quark Gluon Plasma, which we know that the strange content, it is larger in the Quark Gluon Plasma than it is in proton-proton collisions. So the coupling of the hadronizing charm quarks to the enhanced strangeness content in the Quark Gluon Plasma relative to proton-proton collisions was expected to give an enhancement in the DS production. And that seems to be borne out in the data at this point. The lambda C over D ratio, so the ratio of the black over the green, if you wish, it turns out to be a little more challenging. And it is large, it is rather large, about 1 in some regions of phase space. In proton-proton collisions, typically 0.5 or less. So there's an enhancement of this ratio, quite a marked enhancement, and it also seems to have quite some structure. And right now, it's not so easy to describe these data from theoretical calculations. Also note that the data itself at RHIC and LHC are rather different. I mean, there are still big error bars, but if you look here, the maximum at 3 GeV is about 1.2 or so. If you would put that here at 3 GeV, it would be up here. So even the data are not possibly different at RHIC and LHC, and that would really make it rather challenging for theoretical models to explain them. So we'll have to see there how things develop, but clearly this is also very important and interesting information on the hadronization, in particular baryons versus mesons. All right, let's spend one slide on the transport coefficient that I advertised so much in the beginning, what the current status of its extraction is. So here is that dimensionless scale diffusion coefficient as a function of temperature. And as I said before, it's related to the inverse relaxation rate. Actually, it's related to the relaxation rate at zero momentum only. And here are various calculations, the perturbative one, which is way too high, and then even those green and blue ones, if you look back to the calculation of the observer, do not do a good job. So you really need to go down to these calculations, red, purple, or even orange, or you can even do a statistical extraction with some model ansatz, and you also end up in this regime down here. So really, from current data, we can already say with a good confidence that the DS has to be rather small, close to the quantum lower bound of 1, and with a value of maybe 2 to 4, so near the critical temperature. As I indicated in the introduction, if you convert this value into a scattering rate, it will be 1 GeV. So the collisional broadening is huge in this quark gluon plasma. It will probably melt the light parton, the up and down quarks and gluon quasi-particles in the medium. The charm quark may even be borderline. So theoretically, at the end of the day, our best bet will probably, our cleanest and most reliable calculations will be for the bottom quark. So we are very much looking forward also to precision bottom data in the future. Now, one thing that one should also point out is since that DS is really at the zero momentum limit, it's not the full story, because we do expect that thermalization rate will be rather strongly momentum dependent, and we also have to have a good control over this momentum dependence if you want to extract the zero momentum limit. And this goes really back to having the interactions under control. You remember the R-dependent potential that I discussed in the beginning. That is via Fourier transform, of course, directly related to the momentum dependence of the potential in four momentum space. And you have to have a good control over that, because in the experiment, of course, it will be mostly finite momentum particles that you observe. All right, so let me then spend a couple of slides looking into the future, where broader theory efforts have been ongoing to improve the accuracy and reliability of the extraction of the transport coefficients. And there have been in the past two of those initiatives, one within the EMI framework reaction task force, rapid reaction task force, and one called the Heavy-Quark Jet working group. The goal of these, or objective of these larger scale efforts of various, combining the expertise and knowledge of various groups, is to get the various components in the modeling of the heavy-quark observables under control: initial spectra, bulk evolution, the implementation of the transport, the transport coefficients with all their dependencies, and hadronization mechanisms. So let me highlight two results from these efforts. One from the EMI task force, where one of the objectives was to get a feeling of how sensitive the results are to the different medium evolutions that people use for the fireball. So there was a prescribed transport coefficient 5 times the PQCD, roughly corresponding to an DS of 6. And then you see the average of all the model results here in blue to give you a feeling for the uncertainty that, that these different fireball evolutions imply. And you see it's not so bad actually in terms of the uncertainty. But what you also see is that all of basically all of these calculations lie significantly above the data in the RAA and below the data in the V2. So from that, one can already confidently say that a diffusion coefficient of 6 is actually by no means enough to account for the experimental observations. The sort of opposite philosophy was adopted by the Heavy-Quark Jet working group, where the main activity was to simplify to the most extreme case the medium by simply asking or defining a QGP at a fixed temperature and certain path length, and send the heavy quark in there and let everybody calculate how that heavy quark loses energy in their model for the transport coefficient. And these models differ quite a lot. So there was one more step done there was a gauging of the interaction strength, so that the RAA would be a prescribed value at 15 GeV momentum. And then you asked, if I do that, what are actually the transport, what is the heavy quark jet transport parameter in such a setup? And you see there is still quite a large spread in the results that you would extract for this Q hat if you fix it here in the different model approaches. But there is some systematic grouping that actually highlights the different ingredients in the calculations. So, for example, the solid lines are the ones which include radiative energy loss. The green ones, these lines are the ones which use perturbative masses in the bulk evolution. And these ones are quasi-particle models. So there's a systematic grouping emerging that, of course, then tells us about how the different ingredients affect the extraction of the transport coefficient. Okay, so that was basically it. Let me quickly summarize. So I argued that open heavy flavor transport is an excellent tool to probe the in-medium QCD force in heavy-ion collisions. The interaction strength, as far as we can tell now, is well beyond perturbative level, and therefore we need more information on where it comes from. And here our source is Lattice QCD data, which can be utilized to constrain the interaction strength. One of the outcomes is that it seems that we really need remnants of the confining force in the QGP at moderate temperatures to account for its strongly coupled properties, rendering it in fact a strongly coupled quantum liquid close to the lower quantum bound in its transport properties. We can make connections to the bulk medium between the smallness of the transport properties in terms of melting of the light hadrons, while hadron formation seems to emerge from that same strong coupling eventually. And this is, of course, just the beginning of the story. Some of the future objectives that we plan to address in our when we resume our workshop in April of next year is to really develop quality criteria for model components that I mentioned before: bulk medium hadronization, the non-perturbative effects, the gluon radiation, and so on. Define uncertainty ranges within those quality criteria, and then be able to quantify the transport coefficient, and thereby also identifying the mechanisms driving them. And as before, upcoming precision data that already taught us a lot in the charm sector will teach us a lot also in the bottom sector, and with more and more different charm and bottom particles to be produced will also tell us a lot about hadronization due to the different charm hadro-chemistry that we see in the experiment. Thank you very much for your attention. Bye-bye.